Welcome to Station Models. This is part one of two videos. For this video, you will need your science notebook, your BFF, your Earth Science Reference Tables, page 13, a pen or pencil, and maybe a calculator. Make sure you turn up the volume. You definitely need to be listening for my explanations in this video to understand what we're doing. You can go ahead and pause the video and set up your notes on page 55. The station models is the title. The learning objective is that the student will be able to determine the weather in various cities by interpreting station models and creating station models to reflect weather in various cities. Sorry about that typo. Be sure to set up your table of contents too for page 55. So the first thing that we should know about is we've been talking about weather a lot, and the people who study the weather are called meteorologists. This is a little bit confusing because the word meteor, a lot of people know, are actually space rocks. Meteors are rocks that are in outer space, and they fall through the Earth's atmosphere and they kind of burn up in the Earth's atmosphere. So the word meteorologist actually comes from that idea that when these space rocks fall through the atmosphere, they burn up. The atmosphere is what meteorologists study. So that's where that word comes from. And meteorologists use these maps. They come up with these. They actually create maps that look just like these. And I've shown you one of these before when we did our pre-assessment. And I told you by the end of this unit, you are going to know what all of these things mean. We've gotten our basic information about weather. We've learned a little bit about humidity and pressure. And now we're going to really kind of dive into what some of this stuff actually means. And they make these things using data. So we're going to take a look at some data today. You've actually collected some data in our lab, in the classroom, and when we went up onto the roof, but a lot of times the data actually comes from our computers. For example, you can use an app on your phone and it tells you how warm it's going to be today, how cold it's going to be tonight, if it's going to rain, if it's going to snow, if it's going to be sunny outside. And we can actually get this same data on the computers. So I can go to a computer and I can look up New York. I can find out what the temperature is like right now. I can find out what it feels like, what the high temperature is going to be, the low temperature is going to be. I can find out what direction the wind is coming from and how fast it's blowing. I can find out what the humidity is, 40%. I can find out what the dew point temperature is, what the pressure is, how far I can see, the visibility. There's so many things we can find out about each and every city. And there are people whose job it is to look at data all over the country and figure out what the weather is going to be like in New York based on that data all over the country. So they look at this data and then they need to put it on one map of the United States, like this one. That can be quite a challenge, right? They actually look at New York City, they look at Seattle, Washington, they look at Houston, Texas, Fort Myers, Florida, and they have to put the temperature, the air pressure, the humidity, the dew point, the wind, where it's coming from and how fast it's going for all of the major cities in the United States, like Williston, North Dakota, where my husband grew up, like Minneapolis, Minnesota, where my best friend Libby lives. They have to put it all on this map. How do they put all of that information on one map? They use something called a station model. A station model is a symbol used by meteorologists to show many weather variables for a location on a weather map. A weather variable are all those things that we just said: temperature, pressure, humidity, wind direction, wind speed. All of those things are called weather variables. in math class, a variable is x, and remember it can equal a lot of different things. It's a little question mark there. So in earth science, a weather variable is something that could represent a lot of different things like temperature, pressure, wind, okay? So they use this thing right here. This is called a station model. It's a model of what the weather looks like at a particular weather station or a weather city. Any kind of city is a weather station, essentially. So like New York City is a weather station. There are lots of places where we have weather instruments, like you saw on the roof of our school. We have a little weather station. In Central Park, there's a little weather station, and it collects weather data for us. And we can make a little model of what the weather is like at that station, and this is what that little model looks like. So that's why we call it a station model. The nice thing about this is that you can show the weather all across the country, like this map right here, for every city, or at least every major city in the United States. And so a weather person, a meteorologist, can look at this map and, for example, right here, let's see, this is in Nebraska. I can look at this station model right here, and I know that the temperature is 4 degrees Fahrenheit. I know that the dew point temperature is -2. The pressure is 1040.2 millibars. Right now they're experiencing no wind, there are sunny skies, and they're experiencing no rain or no snow. I can tell that just by looking at that little weather station model. And meteorologists are skilled at that. And then they can use this data to predict the weather in different cities. So here's your first check for understanding. Why are station models an important tool for meteorologists? Okay, hopefully you got that question right. Now what we're going to do is I'm going to teach you how to interpret that station model. Just like what I did for Nebraska, I'm going to teach you how to do that as well. So you're going to need your BFF open to page 13 for this. So this is the page, this is the little section, this is at the bottom of page 13 in your BFF. And the first thing you should know is that this right here is what an actual station model looks like. It's got a little circle with a little line sticking out of it. Sometimes it has these little, we call them feathers, sticking out from here, like kind of like an arrow has feathers on the end of it. And then it's got a bunch of numbers and some symbols around it, okay? And this over here, off to the right-hand side, in this box, this is the explanation of what is in the station model itself. The other box that we're going to use for this is down here in the box labeled present weather. That's going to be some information we need too. Okay, so follow along with me as I interpret the following station model using the BFF. And you can rewind this video if you don't understand why I record certain things. You're going to have a chance to interpret the next station model on your own. So you definitely want to be able to understand this. So let's start off with the temperature. So if I want to know what the temperature is, I need to look and find out which one of these little numbers or symbols on this station model here represents the temperature. So what I do is I go to my BFF and I look for where it explains temperature. And if I look at my station model explanation, I see temperature right here. So this number, which corresponds with this number here on my station model, it's always going to be in the upper left corner of this circle. So the circle is there, and in the upper left-hand corner, that number is always going to be the temperature. And it is always going to be represented in degrees Fahrenheit. So when I come back here to my station model, in the upper left-hand corner, I'm looking at that number, 65. So that is my temperature in degrees Fahrenheit. Next up is the dew point temperature. So again, go back to your Earth Science reference tables and see if you can figure out where the dew point temperature is on this station model. So if you look here, I found dew point right here. So that means the number in the lower left from my little circle here, wherever the circle is, in the lower left-hand corner, 27 is my dew point temperature, and it's always going to be in degrees Fahrenheit again, just like our temperature was degrees Fahrenheit. So if I look here at my model in my example, now when I look here, I see that my number in my lower left-hand corner is down here, and hey, it's exactly the same temperature as the regular air temperature for my dew point. So it is also 65 degrees, but I'm using this number down here in the lower left of my big circle. Next up is the barometric pressure. This one is the most challenging for students, but there's a really easy rule that we're going to use for this. So find where it says barometric pressure on your BFF on page 13. So hopefully you found barometric pressure right here. This time it's the number in the upper right hand part from the circle, right? So if you go upper right hand part of the circle, this 3-digit code is the barometric pressure. Now, this is where it gets a little challenging because you can't just take that number and write it down. You have to convert it. The actual barometric pressure for this particular station is 1019.6 millibars. The reason they don't write out this whole number here is this is a lot. This is a big number. They're trying to make this station model really small so that way they can fit a bunch of them on a map. If they wrote out this huge number, then this station model wouldn't be that small. So they make this digit, this code, only 3 numbers long, so it takes up less space. And then you have to follow a couple of really simple rules to make sure that you convert it properly. The easiest way to do this is just to realize they have just taken the last 3 numbers, 196. And I've completely obliterated that number, so let me write that again. Let me circle that again. So they've taken just the last 3 numbers, 196, and that is what they use for the code, okay? This 10 that is in front of it is they just get rid of that. And then they also get rid of this little decimal point here, okay? So if you want to take this code and convert it into an actual barometric pressure, you have to add a 10. Now, it's not that simple because it's not always 10 that gets added in front of it. It's going to be either a 10 or a 9. So you might be wondering yourself, well, how do I know if it's a 10 or a 9? Really easy. There's a pressure scale right next to this in your BFF that we just looked at yesterday, or I should say we just looked at in class. If you put a 10 in front of this number and it shows up on this chart, then you did it right. If you put a 9 in front of this number and it does not show up on this chart, then you did it wrong. It's that easy. So once you put this number in front of it, look it up here on the pressure chart right next door to it, and if it shows up, then you did it right. So let's go back to our example and see what our pressure should be. So here's our pressure number. Remember, it's in the upper right-hand corner from our circle, and this time it is 962. Remember, we either need to put a 9 in front of that, so it would be 9962, and then we have to put a decimal between the last 2 numbers, or it could be a 10 in front of that number. So it would be 10962 with a decimal between the last 2 numbers. So if you look this up on your chart, your scale, your pressure scale, you should see that 9962 shows up on the chart, but 1096.2 is too high. The chart doesn't go up that high. So I know I can't put a 10 in front of it. I know I have to put a 9 in front of it. So my barometric pressure should be 996.2 millibars. The next thing is called the barometric trend. So find out where it says barometric trend in your reference tables, and let's see if we can figure out what to write here. All right, so here is our barometric trend. It's always going to be right underneath our barometric pressure. So it's going to be exactly to the right of our little circle here, right in the middle, I guess, because there should be a number down here as well. So this number is always either going to have a plus in front of it. A plus means that the pressure has been rising. The word trend just means what has it been doing in the past 3 hours. And this is helpful because if it's been rising in the past 3 hours, that tells me that the weather's probably getting nicer outside, sunny, or no clouds. But if this little symbol is a minus sign, that means that it has been dropping. So it hasn't been rising, there has been a drop in the last 3 hours. And that is really helpful for meteorologists because if the pressure has been dropping or getting lower in the past 3 hours, it probably means it's starting to get cloudy out and it's probably going to rain or snow. And then this number tells you how much it has risen or dropped in the last 3 hours. Now again, they are trying to reduce the amount of numbers and stuff that they put on this station model. So they only say 1-9 here, but you have to put a decimal point in between because this doesn't tell me that the pressure has risen 19 millibars. This has risen 1.9 millibars. The reason they do that, they're trying to reduce the number of decimal points here because sometimes decimal points look, they're a little hard to see on a station model. So they're trying to reduce the number of decimal points they have on this station model. So let's go back to our example and see if we can figure out what the barometric trend is. All right, so here was our pressure. So that must mean that this is our barometric trend number. So this time we have a minus, which means it's going to be dropping, if you remember. And this is a 1-9. And if you remember, we have to put a decimal in between the two numbers. So it should be 1.9 millibars. So we would say that this has been a steady 1.9 millibar drop in the past 3 hours. We say steady because this little symbol here, that little slash mark, just means that it's a steady drop, meaning in the past 3 hours, it's been steadily dropping. It hasn't just like dropped in the first hour and then stayed the same for the next 2 hours. It's just been steadily like maybe 5 millibars or 0.5 millibar drop every hour or so. All right, our next one is cloud cover. All right, the amount of cloud cover tells us right here at the top refers to this circle. So we've been referring to this circle, but we've never explained what this means. The cloud cover, it tells us how much of the sky is covered in clouds. So in this case, we've got 75% of this symbol is filled in. And because 75% of it is filled in and only 25% of it is not filled in, we would say that 75% of the sky is covered with clouds. And so that's what that means. Basically, scientists look up at the sky and they say, oh, it's mostly cloudy, and mostly cloudy would be 75% covered. So let's go back to our station model and see how much cloud cover there is. So if we look at our circle, all of our circle is filled in. That means that the cloud cover should be 100%. So if you were to look up at the sky, that means you don't see any blue sky coming through at all. The entire sky is filled with clouds. Next up, visibility. Visibility is on the right-hand side, right here. Okay, so the visibility tells us how far can you see in terms of miles. And this is really helpful for people who are flying planes or who are driving. If you can see for a really, really long ways, this number, the biggest this number can be is about 10 miles. That's as far usually as you can see if the visibility is really good. Usually the visibility gets smaller if it's snowing or if it's foggy or if it's raining and you can't see very far out in front of you. And this can be a problem if you're flying or if you're driving. So let's see what it is for our visibility on our example. So visibility on our example is right here, and that is 1/4, which means we can see 1/4 of a mile or 1/4 of a mile. So that's not very far, which kind of makes sense. It's cloudy, so maybe it's raining, and so maybe we can't really see very far. All right, next one is our wind speed. So let's see if you can find that on your station model in your Earth Science reference tables. Okay, so wind speed is here. The wind speed is indicated by these little things at the end of this stick here. The stick actually represents the wind direction, and these little things at the end, we call them feathers. So these little feathers, it's kind of like the feathers at the end of an arrow. Like if you were to draw an arrow, these are the feathers at the end of an arrow, and so that's why they call these feathers. So if you have a whole feather, like this one, it's a long feather, that equals 10 knots. And if you have a half feather, that equals 5 knots. Since this one has a whole feather and a half feather, we add 10 knots and 5 knots together, so our total wind speed is 15 knots. You might not be familiar with a knot. A lot of times they use these out at sea, like if you're out on a boat, they will say the wind speed is 15 knots. For us, I just think about a knot as being really close to about a mile per hour. A knot is a little bit less than 1 mile per hour. A mile per hour, it equals 1.15 miles per hour, 1 knot, but they're pretty much the same. So if you think to yourself, this is 1 knot or this is 15 knots, it's about 15 miles per hour. All right, let's go ahead and do the wind direction at the same time, because sometimes they'll say the wind direction is from the south at 15 knots. So in this case, this little stick here is coming out of our circle and it's pointing southwest. So if I draw my little compass, north, south, east, west, remember we want this to spell we instead of you. Remember it's not you, otherwise that means you got east and west mixed up. So this is going in the southwest direction. So since this is pointing toward the southwest, that means that the wind is a southwest wind, and winds are always named from the direction that they're coming from. So we would actually say that this wind direction is from the southwest, and it's from the southwest at 15 knots. All right, let's go back to our example station model and see if we can figure out the wind. All right, here's our little stick coming out of our circle. And if we again think about north, south, east, and west, this is going in the upper right hand direction, which means it's northeast. So that means my wind direction is coming from the northeast. And the wind speed, let's see, I've got a whole feather, which is 10, another whole feather, which is 10, and a half feather, which is 5. 10 plus 10 is 20, plus 5 is 25 knots. So my wind is from the northeast at 25 knots, which is about 25 miles per hour. That's a pretty good wind. We're not going to like that so much if it's a cold day out. All right, the last couple of things are really easy. The next one is present weather. And the last one is precipitation. So we're going to do those together. Okay, here's our present weather. It's pointing to this little symbol right here that is in between the circle and my number for visibility. That little symbol, you have to come down here to this box filled with a bunch of present weather symbols. And you need to find that little symbol and figure out what the weather is like. That's a little star, which is right here. So that tells me that it is presently snowing outside. Aha. It could also be drizzling. A drizzle is just light rain. It could be raining. We could have sleet, which if you remember is frozen rain that falls through the sky. It could be freezing rain, which means it's raining, but that when it hits the pavement, it freezes and it forms a sheet of ice. It could be smog, which is actually a combination of smoke and fog. A lot of times you get smog. We think of like this happens in cities where it could be pollution. You get a lot of smoke from smokestacks mixed with fog. And you could get regular fog, right? Which is basically just a cloud on the ground. Hail, remember we talked about how you get hail, these solid little balls of ice that fall from the sky. Thunderstorms, which kind of looks like a weird looking R with an arrow on it. Haze, which is very similar to smog. You could have rain showers, which again is light rain, or snow showers, which is light snow. And the last one, before we go back to our station model, is precipitation. Precipitation, remember, is rain, snow, sleet. So we want to know how much we've had in the past 6 hours. So this will tell you, in this situation, it says 0.25. In other words, 0.25 inches have fallen in the last 6 hours. All right, so let's go back to our station model and see if we can figure out precipitation and the present weather. All right, our present weather symbol, remember, is off to the left between our circle and our visibility number right here. So there's our little present weather symbol. And if you remember, that little R, weird shaped R with an arrow at the end, is thunderstorms. So right now at this station, this weather station, these people are experiencing thunderstorms. They'll probably get some lightning with that. And then precipitation, remember, is this number in the lower right-hand corner, 0.50. So that means they've gotten 0.50 inches of rain. Yeah, because it's been thunderstorming. So they've gotten 0.50 inches of rain in the past 6 hours. Or in other words, this is a half of an inch of rain in the past 6 hours. Whew. Nice job. That was a lot that you just learned. So I want to give you a chance to try this on your own. Go ahead and interpret this station model using your BFF. And if you get stuck, if you're not really sure, you can go back and rewatch the video before you submit all of your answers. Good luck.